coming week we will be learning about energy and enthalpy and the units of energy and how to calculate the amount of heat released or absorbed by a chemical reaction or process. And so to start out, I want us to look at some of the units of energy that we might see, or the units of heat, which a lot of times we'll see the energy in the form of heat. So you may have heard of a joule before, but this is a unit of energy that is very common in chemistry because it's typically the one we're going to use in our calculations. So this is a unit of energy for most equations that use energy. Okay. And we're going to learn how to convert joules and calories today. So if we have calories, that is something that we're more familiar with. And when you're talking about calories with a lowercase c, that's actually different than a calorie with an uppercase c. A calorie with an uppercase c is really a kilocalorie. And if we remember the prefix kilo, that means 1,000. So it's 1,000 calories. So what is an actual calorie? The lowercase c calorie is the amount of energy it takes to raise the temperature of 1 gram of water by 1 degree Celsius. Okay, so this is a unit that's based on water, a property of water, and water takes a certain amount of energy to heat up. And so a calorie is based on that, 1 gram of water to increase by 1 degree C. Okay, so if an uppercase calorie is 1,000 lowercase calories, this is actually the one that we see when we see on a food label. They're really talking about uppercase calories, even though when you read it on there, it might not say necessarily uppercase, but up here on this food label, it does have an uppercase C. So that's consistent. Okay, so our conversions here are that 1 calorie equals 4.184 joules. So that means 4.184 joules is the amount of joules it takes to raise 1 gram of water by 1 degree Celsius. And 1 uppercase calorie, like we already said, is 1,000 lowercase calories. Okay, so those are the relationships we'll use to do unit conversions between different types of energy. So when we talk about energy, and especially in chemical reactions, some reactions will actually release heat, some will absorb heat, and so we have different terms that we can use to describe this. But before we do that, we need to remember what is a system, what is the surroundings, and what is the universe. So your system is anything that you're actually studying. So if you're doing a chemical reaction in a flask, which is usually the case in chemistry, that flask would be your system. Anything outside of that flask, the whole universe outside of that flask, would be your surroundings. But something that's in closer proximity to your flask obviously is more important when you're thinking about the surroundings. And then the combination of those two things we consider the universe. So if a reaction is endothermic, it is taking energy in from the outside. That's what the prefix endo means, and therm has to do with heat. So it's taking energy in the form of heat from the outside. So when you experience something endothermic, it is removing heat from anything around it, from its surroundings. So actually your hand, it will be taking heat from your hand, and so your hand will experience a feeling of coldness. So if you have a cold process or reaction, it's endothermic. Exothermic, on the other hand, just like we know the prefix exo means outward, it's the system releasing heat to the external surroundings. And so if you're holding this flask in your hand, this reaction will feel warm. And the heat will be considered less than 0. So this is why it has Q smaller than 0. So this means you'll get a negative delta H. We're going to actually learn about this Delta H is our enthalpy, so negative enthalpy. That means it's releasing heat. Okay? And so this will feel hot to the touch, or warm if it's not very reactive. Okay? Since over here for our endothermic it says Q is greater than 0, we'll have a positive delta H, so positive enthalpy. Okay. All right, so we can actually calculate the amount of heat, which is the same thing as what we were talking about, the calories that are in food. That would be the amount of heat provided by a substance upon digestion, or the amount of energy that's contained within the bonds of that chemical mixture. So one thing that we need to know to be able to calculate this is the specific heat. Specific heat is a property of a material and it's the amount of energy to raise 1 gram of that material by 1 degree Celsius. So we already saw that a calorie is the amount of energy it takes for water to be increased by 1 degree Celsius. But the specific heat could be talking about any material. So then it would be 1 gram of whatever material you have. So if you wanted to know the specific heat of aluminum, you'd have to measure the amount of energy it takes to raise 1 gram of aluminum by 1 degree Celsius. Okay, so we'll use this heat equation to actually be able to calculate how much heat there is. We need to know what all the variables mean. Q stands for the heat, and that's going to be in joules. Okay. M stands for the mass, which will be in grams. C is our specific heat, and the unit of that should be joules per gram degrees C. And then delta T, this little triangle means delta. Delta always means change. That's going to be our change in temperature for T2 minus T1 if you have two different temperatures. Okay? So let's do this example problem before concluding. During the early morning, a 20 milliliter sample of seawater was collected and left to sit in the sun. Initially, its temperature was 12 degrees Celsius, but after 6 hours, it was 21 degrees Celsius. If the specific heat of water is 4.184 joules per gram times, I should say, degrees Celsius, how much heat was absorbed from the sunlight? Okay, so if we're looking for how much heat, that means that we're going to be looking for Q. That's our unknown, Q. We're given two different temperatures. So our initial temperature here, that's our T1. Our final temperature here, that's our T2. We're given a volume of water, 20 milliliters of water. That's probably going to be used to get our mass. So how many grams of water are in 20 milliliters? If you recall, 1 milliliter of water is 1 gram. So 20 milliliters would be 20 grams. That's our M. Okay? And finally, we have our specific heat here. Specific heat is C. So we have everything we need to be able to calculate Q. All we have to do is plug them into the equation. So we have Q equals, let's see, M comes first in there, so let's put 20 grams, that's our mass, times C, we have 4.184 joules per gram degrees Celsius, and then times our change in temperature. So that means if it's a change, we're going to have to subtract T2 minus T1. So our T2 was 21, our T1 was 12. So 21 minus 12. It's important to do that subtraction before you multiply things out. So we're going to get 9 for a temperature change. 9 degrees C times 4.184 times 20. And so I need to get a calculator out. Let's see, 9 times 4.184 times 20, and I get 753 joules. And I could keep less sig figs because I have fewer sig figs in my initial information, but we'll just keep this for now. This is the amount of heat that was absorbed by this water as it was sitting in the sunlight. Okay. Finally, we can do an experiment to actually measure what the amount of heat absorbed by a solution is. And we can do this using a setup or an experiment called calorimetry. This is a technique. And so you can do this in a coffee cup even if you have it insulated pretty well. So a lot of times people will use multiple coffee cups to insulate it very well. And all you need is whatever solution that you're measuring the change in, so it could be a reaction or something like that, and then you need your thermometer. We're going to do something a little bit simplified but related to this in class this week. But this is a technique for measuring heat absorbed or lost. Okay, and so let's look at this example. A calorimetry measurement of a simple reaction in 100 grams of water gives a temperature change from 25 to 27 degrees Celsius. How much heat did the reaction produce? So right here, we have our temperature change. So they would have measured it on their thermometer, say it started here at this temperature and went up to that temperature. So that's the difference in how much heat was produced in this reaction. And I'm saying heat was produced because the temperature increased. So that means that this is an exothermic process. It's releasing heat to the surroundings. The water is the surroundings. Okay, so in this reaction we used 100 grams, that's our mass, that's our delta T. Then finally, the specific heat is the only other thing we need to know, and we know for water it's always 4.184. We're measuring the difference in temperature of water. So if we want to find our Q for this, all we have to do is plug in our numbers. 100 times our 4.184 times our difference right here is 2 degrees Celsius, and we'll get our heat produced in joules. So let me calculate that really quickly. 2 times 4.184 times 100 grams, and I get 837 joules. So this would be the amount of heat produced by that reaction based on the amount of water that I have in the cup. Okay. And that's all we have for today. So just make sure that you read the reading and use that as the video as supplement to the reading, so hopefully you can understand all of the content that's going on in class this week with our experiments and our heat calculations. And let me know if you have any questions about anything in this video as well. All right?